All right. So we were working last time on the last part of chapter 6 on frames and machines. And we just went through a simple machine here where we had a couple of pulleys and we figured the force on the pin at B. And also the force that was needed to lift the stone. This one's a little bit more complex machine. It's a pole pruner. So the way this machine works is on the end of a pole is a knife edge here, and it pushes against, this is either another knife edge, so they would be a bypass pruner, or this would be a blunt end that the other knife would just push up against. And it's hard to tell really from this angle which type it is, and it doesn't really matter, because what we're doing is we're exerting a force on this branch that's going to cut it. And we exert a force through this lever that's then attached to this pulley that's attached to the rope that's down at the end of the rope. So we see here that the person operating the pruner is exerting a force of 50 newtons by pulling on the rope. So what are we asked for? If the force 50 newtons acts on the rope, determine the cutting force. What is that? Determine the cutting force on the smooth tree limb at D and the horizontal and vertical components of the force acting on the pin at A. The rope passes through a small pulley at C and a smooth ring at E. So as before, we're going to want to break this down into more manageable sized pieces. And before we even get started, can you see any two force members that are going to be acting in this machine? Note the knife part here is part of this rigid member. So it's going to have a force at B and a force at A and then a force on the branch at D. So there's going to be three forces on that piece. Okay, well the tension, the rope is always in tension, so it's in tension everywhere. So from this point of attachment up through the pulley and down to the end, that's all one tension force. So the smooth ring here and the pulley is just changing the direction of that tension force. There are two places on there where there are two force members, so we should identify at the beginning because it's going to make our life a lot easier. Pardon? The branch itself, that's going to be a two force member because we're told that these are smooth, or sorry, that the tree limb itself is smooth, so there's not going to be any friction on here. Not really realistic, but as long as these forces are perpendicular, it doesn't matter whether it's smooth or not. It's once we start to cut that there would actually be a friction force, and this angle changes. So that's going to be a two force member. So the branch is, two force member in compression. All right, there's at least one other two force member in this machine. Oh, A is just a pin. So two force members, an element that's going to have only two forces on it that are going to be collinear, so it's either going to be in tension or compression. BC, the link BC here is a two force member. It only has the force on the pin at B and on the pin at C. that's going to help because that tells us what the direction of the force on pin B is going to be on this cutting piece. Just make a note on here, link BC is a two-force member in tension. All right. So we know that we've got a tension force in the rope of 50 newtons. Where should we start? Right. We should start with a free body diagram of the pulley at C, or the pulley and pin at C. Okay, so if we draw a circle there to, whoops. What have I done here? So make it a little bit bigger. There's C. What forces are acting on the pulley and pin at C? Right, we've got a tension force from the rope on either side of the pulley that are both pulling down. Oops. And they're both pulling down at the same magnitude of 50 newtons. And what else? We've got the reaction force of the force BC. So that's going to be, because BC is in tension, that's going to be pulling up. So label those T equals 50 newtons and FBC. Normally I'd write the equations of equilibrium, but this one looks pretty simple. What's FBC going to be equal to? FBC is going to be equal to 2 times the tension force, equals 100 newtons. All right. Now what are we going to do? Okay, before I do that, I need to identify the next object for my free body diagram and equation of equilibrium. So what object are we going to use next? Right, so we're going to use DAB, or BAD. BAD sounds better, so BAD. So 2, free body diagram of BAD. All right, so I'm just going to trace BAD so I can copy it down below. It doesn't have to be perfect. Just has to be the same general shape. All right, so what forces do we have on BAD? So this was B, this is A, and this is D. We have the tension force at B, so if BC was in tension, what direction is this force going to be in? It's going to be down. Okay, so I can label that FBC equals 100 newtons from before. All right. We're going to have a normal force at D, and we said that the branch D was in compression. So if it's in compression, then this force is going to be to the left. That's one of the unknowns we're looking for. Okay, and we're going to have reaction force at the pin at A. Don't know the direction, so we would draw that in with both x and y components and then solve for both. I'm going to draw these in as if they're both in the positive x and positive y direction. If we look closely, we probably guess that one of those is wrong. That's okay. If we guess wrong, we're just going to get a negative answer, and then we know that it's in the opposite direction. So label this one A, AX, and AY. All right. Equations of equilibrium. Okay, so we have three unknowns. We're going to need three equations. So we're going to need a moment equation. So the suggestion was to take the moment about A, and that's a good suggestion because that gets rid of two of our unknowns. I could find AY from some of the forces in the y direction, and then I only have two unknowns, and then it doesn't really matter whether I use D or A. But let's start with the moment about A. So that was 30 millimeters and 100 millimeters. We should put that on the free body diagram as well. So this distance here, that's 30 millimeters. And this distance was 100 millimeters. Okay, so if we're looking at sum of the moments about A equals 0, what's causing a moment about A? Okay, so I've got FD times 30 millimeters is going to cause a counterclockwise or a positive moment. You can leave it in millimeters. Excuse me. So 30 millimeters FD, and then I have FBC that's creating a clockwise or a negative moment. So minus 100 millimeters times 100 newtons. All right, so we can solve that one for FD. $333 newtons. All right, And then to find the forces on the pin, we use the other two equations of equilibrium. Net force X equals 0. So right now I've got FD, which is 330 newtons, 333 newtons, plus AX. So that tells me AX is actually going to be in the opposite direction. So negative 333 newtons. And net force Y equals 0 equals AY minus the 100 newtons. So that gives me AY equals 100 newtons. All right. So it actually wasn't that hard once we broke it down into pieces. What would the mechanical advantage of this hole pruner be?
You only had to pull with 50 newtons.
That's right. We exerted a 50 Newton force to exert a cutting force of 333 newtons. Yeah, so 6.66 would be our mechanical advantage. Which also means you're going to have to pull that rope a lot farther than the width of the branch, but that's not really a big problem to pull the rope farther. Usually the limiting factor is the amount of force that you can put on the branches. All right, so the next problem, is this our last one? Nope, second to last one. Here we have an interesting looking beam. It's got one side here that's cantilevered out, and then there's a link here, a BC link, and then there's another half of the beam that's pinned to the other wall. And we might do that to make sure that the beam isn't over-constrained. So if this beam stretches or shrinks slightly because of either because of the loading, because of bowing, because of the loading, or because of temperature change, then this link's going to allow that to happen without putting additional stress on the beam. So in this case, when it's at equilibrium here, we want to determine the components of reaction at the fixed support A and at the pin D. We can't just treat it as a rigid body because it isn't. It's got this link here in the middle. So what should we look for first? Two force members. Are there any two force members? This link here between the two halves of the beam is a two force member. So the link BC is two force member. Do you think BC is going to be in tension or compression? It's going to be in tension. But if you can't tell that it's in tension and you assume that it's in compression, that's okay too, because you're just going to get a negative answer. But it is going to be in tension because that's the only way that the other end of this pinned end beam is going to be supported, is if BC is lifting up on this side, which would mean that it would have to be in tension. If you didn't see that, don't worry, you'll get better at recognizing it. And it doesn't really matter, because if you assume the wrong thing, you just get a negative answer. All right. Which side do you think we should start with? the right side. The right side is going to be the better choice. Why is that going to be a better choice?
It's only a pin joint with
Right. So the answer was to solve for the BD, or the right half of the beam, which is BD, because then there's two unknowns at the pin joint, so an X and Y reaction force, and there's the two force member in the link BC. So three unknowns, we have three equations of equilibrium. We should be able to solve it. If we started with the left side, AC, then we actually have three components of reaction at A. Because it's a fixed joint, there's an X component of reaction, a Y component of reaction, and then a moment component of reaction. So there's three unknowns there, plus this one makes four. So we could set up the equations, but we can't solve them. So better to start with the simpler side. So do a free body diagram of E D. And this time I'm going to cheat. I'm going to, there we go, take a picture of BD. All right. So I've got my 10 kilonewton force. What other forces do I need to add to BD? All right, we've got our two force member BC here, which if it's under tension is going to be lifting up on this side. Call that one FBC. And our reaction components at D. So we can call that dy and dx. All right, from that free body diagram, we want to go to our equations of equilibrium. Okay, I'm going to start with that force X. What forces are acting in the X direction? Well, nothing, but by our diagram we have dx. So dx has to equal 0. If I write net force y equals 0, that's going to give me these two upward forces. So that's going to be dy plus FBC minus 10 kilonewtons equals 0. So that's an equation with two unknowns. How am I going to figure out, other than method of staring, which I'm pretty sure we can all figure out that these are going to be 5 and 5, but that's not part of a complete solution. Right? A complete solution is demonstrating that they're 5. So we could do moments about D, or we could do moments about B, or we could do moments about the center here. Any of those are going to give us the answer we want. So D would be a natural choice because there's actually two unknowns here, even though one of them is 0. If we'd done moments first, we wouldn't have known that. So if I do moments about D, the 10 kilonewton force is going to be a positive moment. So it's going to be 1.5 meters, 10 kilonewtons. And then FBC is going to be a clockwise or negative moment. So minus, that's a total distance of 3 meters. And that gives us FBC equals dy equals 5 kilonewtons. All right. So that finishes the right hand of the beam, the right hand side of the beam. Now we'd move over to the left side. So I'm going to need another page here. So the left side of the beam is AC. Okay, and I'm going to cheat again. All right. So what forces are acting on the left side of the beam AC? This is C up here. Right. There's going to be the tension force from FBC, but because it's lifting up on B, which is underneath, it's going to be pulling down on C. So that's FBC equals 5 kilonewtons. And the reaction forces and moment at A, since it's a fixed joint. So we would have AY, AX, and then here's a different color. MA. All right, and then how are we going to find those? 3 equations of equilibrium. All right, so net force X equals 0. And again, there's only one force, so it has to be equal to 0. Net force Y equals 0. So in the Y direction, I've got my support at A. I've got the 12 kilonewtons down. And I've got the 5 kilonewtons down. Okay, so that gives us AY. 17 kilonewtons. Okay, and then our last equation of equilibrium, we're going to get our reaction moment here. So the sum of moments about A equals 0 equals the couple moment, MA. And this 12 kilonewton force, is that going to produce a positive or a negative moment? Negative. So that would be minus 1 meter, 12 kilonewtons. And minus, that's a total distance of 4 meters. Kilonewtons. Okay, so we solve that. MA is going to be positive 32 kilonewton meters. So that means it's in the direction that we showed, or counterclockwise. All right. That's not the same reaction that we would have if it was just a single cantilever beam. Like putting that link in the middle has changed the loading on this fixed jointed A. And where I put the link is going to also change the loading on A. Okay, here's our last question for this chapter. So this says the wall crane supports a load of 700 pounds, and we want to determine the horizontal and vertical components of reaction, I should say at the pins A and D. And also, what is the force in the cable at the winch W? Okay, so we can see we've got an electric motor here that's operating a winch that's lifting up the 700-pound load from this hook. So before we do anything else, are there any two-force members here? DB, right? This is going to be a two-force member. Does it look like it's in tension or compression? I would say that it's going to be in tension. All right. Where would we start for this one? Okay, so we could look at this whole, the hook, pin and pulley at E. Do a free body diagram of that. Okay, so I got 700 pounds down. And I'm going to have two tension forces up. Try to make them a little bit more vertical. That's better. Okay, and again, we could write the equations of equilibrium, but this one's, I think, simple enough that we can all see that T is going to be equal to 350, half of the 700. All right. What do we want to do next? Okay, so C, what are we going to do a free body diagram of at C? The pulley and the pin. Right, we'll group those together. Let's see. All right, what forces do we have on the pulley and pin at C? Tension forces in all of the ropes. So we're going to have 2 down and 1 to the left. And we're going to have the reaction force at the pin. So the reaction force at the pin is going to have both X and Y components. So call that CY, CX. This is T, and this is T. So if we look at our forces in the X and Y direction, what have I got in the X direction?
Yeah.
CX, and then T is in the negative X direction. CX equals T equals 350 pounds. That force in the Y direction equals 0. What have we got in the Y direction? I got CY, which is up, and 2T that are down. Therefore, CY equals 2T equals 700 pounds. All right. What next? You want to do the pulley and pin at B? How many unknowns do I have there? There's going to be 3. There's 3 because we're going to have the X and Y reactions of the pin. Actually, if we're only looking at the pulley, then there's only going to be 2. So we can look at the pulley and the pin separately. And then we'll have to add that force when we do the free body diagram of ABC. So we can do the pulley and pin at B. So that'll be 3. All right. So what forces do we have on the pulley and pin at B? Ignore these members. So we've got tension in the rope again. So that's going to be in this direction and in this direction. And the reactions on the pin, which we don't know its direction, but we know there's going to be an X and a Y component. So this is T, and this is T, and this is BY and BX. And that angle was 60 degrees. So that means that is 60 degrees. All right, what have we got acting in the x direction? We've got Bx, and we've got the tension, which is 350 newtons, or pounds. And then we've got the x component of this tension force. So that's going to be minus 350 sine cos 60. Alright, so what's Bx going to be equal to? Negative 175 pounds. So Bx isn't actually to the right, it's going to be to the left. Alright, what have we got acting in the y direction? We have By, which is up, and then we have the y component of this tension force that's going to be down. So minus 350 pounds sine 60 degrees. $303 pounds. All right. What next? Ultimately, we're looking for the forces on these two pins. Pardon? Right, if we do a free body diagram of the beam ABC, the only forces I don't know on that now are the reactions at A and the force in this two-force member. So that gives me three unknowns I can solve with my three equations of equilibrium. So I need another page for that. Alright, so we're going to have our free body diagram of beam A, B, C. Okay, so we're actually only looking at the forces on the beams. I've got the pulleys in here because I copied it from the other diagram, but instead of having the forces on the pulleys, we're going to have the forces that the pulleys exert on the beam. So there's going to be x and y components at B and C. And what do we know about the x and y components at B and C compared to the x and y components we have at B and C here? Same magnitude, opposite direction, because they're the action-reaction pairs. So Cx is actually going to be to the left, and Cy is actually going to be down. Draw those ones in first. So Cx is to the left. Oops. Cx, Cy. Bx was calculated as being to the left, which means it's actually going to be to the right. And By was calculated to be up, so that means it's down because it's the reaction. Okay, so we know all four of those forces. Okay, so this was Cy equals 700 pounds. Cx equals 350 pounds. That's in that direction. Bx equals 175 pounds. And By equals 303 pounds. Okay, so what other forces are acting on the beam? The reaction forces at A, so they're going to be of X and Y components, and the two force member BD. Oops. Okay, so if we label those, call that AY, AX, FBD. Okay, so the Bx I drew here to the right, but we actually ended up with a negative value. So it was to the left on the pulley, which means it's to the right on the beam. So that's why they're drawn in the same direction, because it came out negative. Okay, good question though. All right, so from the free body diagram, we want to go to equations of equilibrium. Which equation should we start with? Which equation can we only have? Actually, there's two of them that would work that I can solve for one variable. Oh, no, there isn't. There's only one that works. Sorry. Moment about A. So sum of the moments about A equals 0. So the first point we get to moving from A is B. Bx produces what moment about A? 0, because it's parallel to AB. By is going to produce a negative moment. So we would have minus 4 feet times 303 pounds. FBD also produces a moment about A. How are we going to figure that moment out? So 4 feet. Is it 45 degrees? 4 and 4, yeah. Cos 45 degrees times FBD, and that's a positive moment. And we go to C, and do either of these produce a moment about A? Only CY. So that's also going to be a negative moment, because it's clockwise. So minus 8 feet, 700 pounds. So from this equation, we can solve for the two force member FBD. Okay, did anybody else get 2,410 pounds? Yeah, anybody get anything different? 2,410 pounds. Once we know FBD, then we can find the others by the equilibrium, the other two equilibrium equations. So net force X equals 0. So that's going to be AX minus the X component of FBD plus, oh, sorry, plus 175 pounds minus 350 pounds. So if we solve that for AX, it should be positive. Anybody at College of the Rockies got a value for this one? $18.79. So 1,880 if we were rounding to 3 sig figs. 1,880 pounds. All right, we do the same thing in the y direction. So we've got AY plus the y component of FBD, so plus 2410 pounds sine 45. And then BY and CY are both negative. So minus 303 minus 700. And then we solve for AY. Negative 701 pounds. All right. And that's I think everything we were asked for. Normally if you were designing a pin for A, you'd want to know what the resultant of these two are, and it's going to be about 2,000 pounds. And then you'd choose a material and a size that was appropriate for that. All right, so that finishes chapter 6, which means we're about a third of a class ahead of schedule. So we're just going to get a start onto chapter 7. So chapter 7 is looking at other types of internal forces. So far we've looked at internal forces where we're able to break machines down into component parts to figure out the forces on the pins, to figure out the tension and compression forces. But what about the material that's in between the pins? Well, we've looked at the tension and compression forces, but there's other forces and bending moments that are acting on those materials between the pins, unless they're a two-force member. So to figure out those internal forces, what we're going to do is we're going to take a part of a beam, or we're going to take a beam and we're going to cut it figuratively in two, and where we cut it, those internal forces become external forces if we're only looking at a free body diagram of half the beam. So this is an example of a beam here that's been cut in half. These are external loadings, and then these are the three components of internal forces that are acting on the beam. So we've got a vertical and horizontal force, and we also have a moment here, because it's basically it's a fixed joint. It's fixed to the other half of the beam. The vertical component here is called a shear force. And it's called a shear force because that's the force that's going to be acting to basically cause that beam to fail in a shear direction. This is a normal force. So the normal force is the forces we've looked at so far, and it's either going to be in tension or compression. This one's drawn in tension. And then this is the moment reaction, and it's called the bending moment. So the magnitude of this reaction, it's not a force, but this reaction moment is going to determine how much that beam is deformed in shape. The normal force might also deform the beam, but it's going to deform it in length basically only. That's why it's nice to have the trusses where they're only in tension and compression, so the only thing that can change is going to be the length of those members. And if we built them properly, their length isn't going to change by very much. So use method of sections to make internal forces into external force, then solving using free body diagram of the section. That's what's shown here. Planar members will have normal force. Shown here is N in tension or compression, shear force, which is, we give the letter V, and a bending moment, M, all acting at the cut. These are all the conventions. We'll go through the conventions in a little bit more detail, but these are all shown as if they're positive. Positive normal force is tension. A positive shear force is actually causing clockwise rotation. And a positive bending moment is causing this top surface to become concave. And we'll come back to those in a second. If we have a 3D member, it's just like in 2D, where we're making the section cut, it's actually fixed to the other side of the beam. So how many components of reaction do we have at a fixed joint, a fixed three-dimensional joint? We would have 6 components of reaction. So there'd be 3 forces, the X, Y, and Z direction. So that's going to be 1 normal force and 2 shear forces. And then we're going to have 3 moments. So the 3 moments are composed of 2 bending moments. So those are the moments that are on axes that are perpendicular to the beam. And then the other one is a torsional moment. So that's causing the beam itself to twist instead of bend. All right, so the sign conventions. Normal force is always positive in tension and negative in compression. Shear force, what is this? Normal force. This is shear force. The shear force V is positive when it causes clockwise or negative rotation. So notice when we look at the 2 sections here, the normal forces are opposite if they're in tension. The left side is going to be to the right side is going to be to the left. These 2 positive shear forces are also opposite. That's because, by Newton's third law, these are action-reaction pairs. If this side of the beam is pulling down on this side of the beam, then this side of the beam is pushing up on this side of the beam. So these 2 positive shear forces are the same force. And M, which is our bending moment, is positive when it creates a concave upper surface. So we can see this bending moment is going to cause this to bend this way, and it's going to cause this to bend this way. The reason for this convention is normal beam loading that's from the force of gravity is going to cause a shear force in this direction, and it's going to cause a bending moment in this direction. You don't normally see beams that are bowed up unless they're cantilevered over the end, and then they would be bowed up. But if it's supported at both ends, then the beam is going to have a concave shape like this. And this is a beam that's got reactions on both ends, so this would also cause concave bending. So that's also positive moments. So on the right section, that's going to be a counterclockwise, and on the left section, that's going to be clockwise. So the procedure. First, find the support reactions before sectioning the member. So how do we find the support reactions for the whole thing? That's exactly what we've been doing since chapter 5. So we do a free body diagram, equations of equilibrium. Okay. Then we would draw the free body diagram of a section. So usually, if we're cutting an object in two, there's going to be a left section and a right section. How do we decide which section to draw? Choose the one that's the easiest. So that's going to be the one with the least number of loads. They're both going to have 3 support reactions, so they're both going to have the same number of unknowns, but one might have more known forces on it to deal with. It's going to take a little while for you to feel comfortable doing this because everything's backwards when you do a right section if you start doing left sections first. It's going to become automatic. Like everything else, the more you do it, the more automatic it becomes. So once you've drawn the section, drawn the free body diagram for the section with the 3 internal forces, then you just solve for the equations of equilibrium to find those internal forces. So here's an example. This is a beam. It's a simple beam between A and B, and then it's cantilevered out here between B and E. And what we want to find is the shear force and moment at points C and D. They're not asking us for the normal force. Can you maybe guess why they're not asking us for that? Because it would be 0, right? If we drew a section here and we had a normal force to represent the tension in the beam at C, it would be the only X force. So it would be 0. Most normal loadings on a beam where the loading is all from gravity are going to have no tension and compression. It's not entirely true. In the center of the beam, there's no tension and compression, but as soon as we put a bending moment on there where the beam is actually changing shape, the bottom of the beam is elongated slightly and becomes a tension member, and the top of the beam is compressed slightly, or compressed, and becomes a compression member. So that's why we're figuring out these bending moments, so we can figure out those stresses that are going to cause failure of the beam. Unfortunately, we don't do that in this class. We get just to the point where we can do it, and then in your strength and materials classes in second and third year, you'll actually start using those. All right, so what's our first step? Find the support reactions where? Right, so find reaction forces at A and B. So we would do that by creating a free body diagram of the whole beam and solving for the equations of equilibrium. So A is on a roller here. So what kind of support reaction are we going to have there? Right, it's only going to be normal to the surface, so it's only going to be in the y direction. And B is a pin joint, which means it could support reactions in the x and y direction. So I think by method of staring we can tell that Bx is equal to 0, but it's important that it's there because without Bx then it's not properly constrained. So Bx equals 0. So how are we going to find Ay and By? Okay, so I could do moments about B to find Ay, or I could do moments about A to find By. Or I could do both. I don't have to do a force equation at all. So if we do moments about B, which forces are going to cause moments about B? Ay, is it going to be a positive or negative moment? Negative. So that's going to be 6, 4, 4, 14 feet. So minus 14 feet times Ay. 500 pounds is going to cause a positive moment, so plus 8 feet, 500 pounds. What about the 200 pounds? No moment because it goes through B. Same with By and same with Bx. 300 is going to be a negative moment, so this distance is also 8 feet, so minus 8 feet, 300 pounds. Okay, did anybody else get 114.3? Anybody get anything different? Nobody's going to say 114.3 pounds. Okay, so then we could find the force at B by using the sum of forces in the y direction, or we could do moments about A equals 0. So if we look at the moments about A, first thing I come to is this 500 pounds. So that can be positive or negative moment. Negative. So that's going to be minus 6 feet, 500 pounds. Next we're going to get to B, which is 14 feet away, and we're going to have the 200 pounds down. So I'll start with that one. So that's going to be minus 14 feet, 200 pounds. And then at A, I also have Ay, which is up, which is creating a counterclockwise or a positive moment. So plus 14 feet, 114.3 pounds. And then the last one we're going to get to is the force at E. So that's a distance of 22 feet. So 22 feet times 300.
That one would be 114.3 because that's the unknown. That's the 114.3 is Ay.
Oh yes, that's right. Thank you. BY, not AY, BY. That's going to be hard to solve for our unknown if it isn't in the equation.
We get 0 equals.
0 equals something that's not 0. So this one was 300 pounds. I'd like to say that I make those mistakes just to make sure you guys are paying attention. But 886, and that's good because then 886 plus the 114 adds up to the 1,000 pounds, which is our total loading. So 8 should be 885.7 pounds. So I'll keep the extra digit in there because that's not actually what we're asked for. All right. So now we want to find the internal forces at C and at D. So if we're doing the internal forces at C, should we use a left section or a right section? For C, we should probably use the left section because that means I've only got these two forces to worry about. So we're going to need another page here. And we'll do FBD of left section. So that's A to C. Okay, AY I know now is, that was the one,
Yeah, the one.
pounds. Okay, so now I would draw in my shear normal and bending moments. So I'm going to draw the normal in here even though we know it's 0. Just for completeness, we're going to draw it in. So this would be N at C equals 0. I'm going to draw the shear force in the direction that it isn't in. I'm going to draw it in as if it's positive. Because we're always going to draw the shear force as if it's positive, and then when we get a negative answer, because it's in the opposite direction, that represents a negative shear force. So we draw the shear force in, down, even though we know that it's up. And then we would also draw in the, let me label that one first. So that'd be V sub C, shear at C. And we'll use a different color, and we'll draw in the bending moment MC. I always draw them in as if they're positive. And we solve as if they're positive, and then if we get a negative value for the answer, then we know that it's opposite. So we would draw, or we would then write the equations of equilibrium. At Fx equals 0, we've already done. That's equal to NC. At Fy equals 0. So in the y direction, I've got this force that's up, 114.3 pounds. I've got the 500-pound force that's down, And then I've got the shear force that's down. Then we can solve for the shear force. So we would probably call that negative 386 pounds for our final answer because 3 sig figs. Okay, how are we going to find the bending moment at C? I could take the moments about C. That would be one option. Could take moments about A. That would be another option. We take moments about any point because this bending moment is a couple moment, right? It represents the tension force that's in the bottom of the beam and the compression force that's in the top of the beam as a couple. So that couple moment then can be calculated anywhere on the beam. C probably is the easiest place to solve it because that gets rid of VC, which we've just calculated, and in case we made a mistake in VC, it's only going to be reliant on the other two values. All right, the way we've drawn MC on the left section, that would be a positive moment. So there's the couple moment MC. And then we get to the 500-pound force. Is that going to be positive or a negative moment? Positive, right? So still, right-hand rule. Still going counterclockwise. So plus 4 feet times 500. And then the reaction force at A is causing a clockwise or negative moment. So minus 10 feet, 114.3 pounds. And that gives me my bending moment. This would be 900 and something. 800 and something? Negative 857 foot-pounds, or pound-feet. Okay, so that means it's going to be in the opposite direction here. That means this part of the beam is actually going to be convex on the top, not concave. Seems a little bit odd, but it's because of the loading of the rest of the beam. That was our time, 9:48. So we're probably not going to have time to finish the other section, but we'll have time to set it up anyway. To find the shear and moment at D, should we use a left section again, or should we use a right section? I think the left section is going to be a lot easier. And it's not just the interest of time, it's the interest of making life easy.
I said left as a joke, but...
Oh, sorry. I thought you meant right. Yeah. I only hear what I want to hear. FBD of right section DE. All right. What other forces do I have on the right section DE? The shear moment and the normal force. So if we're assuming positive direction, which direction would I draw the shear force? Because it's a right section, an upward force would cause clockwise rotation. What direction do I draw the normal force? Normal force would be to the left because we assume it's in tension. Normal force we know is going to be 0. What direction do I draw the moment, the bending moment? This time the bending moment would be drawn clockwise because that's what would cause this top surface to be concave. Whoops. That's MD, VD, and MD equals 0. All right, so we'll solve for VD and MD next time.
Probably be really complicated
It'll take about a minute.
because they're not like negative 300 and minus 600.
That's exactly right. Yeah.
Yeah, no.
So what does VD represent physically?
The shear force.
Okay. So that's like where it goes to the like how much we're trying to sort.
That's right, yeah. As opposed to how much they're pulling. So it's the vertical component of the reaction force, the perpendicular component of the reaction force.
Yeah, I was confused because it's shear like that.
Yeah, it's shear like that.
Yeah. That's weird that on the first one it'd be convex. Like
The second one's going to be convex too, but if you look at the loading, it's because it's got that overhang.
yeah.
That's what's going to cause it to go convex.
Okay.
It's like one big convex.
Yeah. If we had some slender wood, we could set up an experiment and see that it's convex.
You are the first person to join the conference.